Super easy if I assume complete dissociation. The problem is that for many weak acids, I can't make that same assumption. Okay? So what happens if I have a weak acid? Okay? For a weak acid, I have to say that HA now is largely undissociated. It will dissociate into H plus A minus. Okay, and I'm going to now define something a little different. I'm going to say my equilibrium constant here is, of course, the proton, the conjugate base, divided by HA. And I'm going to give this a special name. I'm going to call this Ka for K acid. And here I have to apologize for the field of chemistry as a whole. Okay? So I forever was confused about this because I always learned that Ka meant K association and Kd meant K dissociation. You guys ever seen that? And then people start talking about Kas, and I couldn't figure it out because it looked to me like this was a dissociation constant. So I apologize for chemistry. Okay? When you see Ka, you have to ask the person that's explaining it, do you mean K acid or K association? And in this class, I promise you, whenever I use Ka, I'm going to be talking about K acid. Okay? So let's do an experiment now with acetic acid. And what I want to do with acetic acid is something like we did with hydrochloric acid, but a little different. What I want to do here is we're going to take acetic acid, and we're going to, which is, as I mentioned to you, right, it's basically, I guess I should write it out. Acetic acid is this. It dissociates to some extent into acetate, CH3CO minus, plus a proton, and its Ka is 1.75 times 10 to the minus 5 molar. Okay? So it's a small number. It only dissociates to a small amount. So the experiment that I now want to do is I want to add 10 millimoles of acetic acid, which I'm going to abbreviate like this, HAC. That's acetic acid. Into 1 liter final volume of H2O. And I want to ask, what's the final pH? Now to do this, I need 4 equations. Okay? Because I can't assume complete dissociation. Okay? So 2 of the equations are determined by equilibria. Okay? So 2 correspond to equilibria. And those equations are that the concentration of protons times the concentration of acetate anion is simply equal to 1.75 times 10 to the minus 5 molar times the concentration of acetic acid. We'll call this equation 1. And of course, the second reaction is nothing other than the ion product of water. Right? That's just the concentration of protons times the concentration of hydroxide anions has to equal 10 to the minus 14 molar squared. That'll be equation 2. Okay? Now I have to add a proton balance. So here's my third equation, proton balance. Clearly, you would all agree that the total concentration of protons here has to equal the 2 sources. It has to equal the acetate anions plus the hydroxide anions. We'll call this equation 3. And then the last equation is a mass balance on the acetate. Okay? You know that I added a total of 0.01 moles into a liter. And this has to equal, therefore, the concentration of acetate anion that I finally end up with, right, plus the concentration of acetic acid that hasn't dissociated. And we'll call this equation 4. Now, I have 4 equations and I have 4 unknowns. Protons, hydroxide anions, acetate anions, and undissociated acetic acid. 4 equations, 4 unknowns. I could plug and chug. Or I could make some assumptions. So, 4 equations, 4 unknowns, plug and chug. Or let's make some assumptions. So the first assumption I think we can make is that it's an acidic solution. And that means that we can probably say that the concentration of acetate anion is greater than the concentration of OH minus of our hydroxide anions, right? And that means, therefore, we can write that the proton concentration total, which we said here was in equation 3, was equal to acetate plus OH minus, is probably about equal to just the concentration of acetate anions. Okay, that doesn't seem so unreasonable. Okay? The second assumption we can make is I told you that acetic acid is a weak acid. Okay? So it doesn't dissociate very extensively. So maybe that means that the concentration of acetic acid at the end isn't that dissimilar from what I added because not a lot of it dissociated. So I can say that maybe this is about equal to the amount I added, 0.01 molar. Okay, and so with those assumptions now, I can go back to equation 1. This is the equation that I'm going to use. And let's see what I get. I can say from that the concentration of protons times the concentration of acetate anions equals 1.75 times 10 to the minus 5 molar times the concentration of acetic acid. I already told you that I'm going to make the assumption that this is 0.01 molar. I'm going to pretend it didn't dissociate. And because the proton concentration is roughly equal to the acetate concentration, I can replace this with proton concentration. This is about also equal to the proton concentration. And so now I end up with a proton concentration squared that's equal to 1.75 times 10 to the minus 7 molar. Okay? And a concentration of protons, if I take the square root, that's going to equal 4.18 times 10 to the minus 4 molar. And if you take the minus log 10 of the pH here will now be 3.38. Okay? So we took H2O, which had a pH of 7.0, and we dropped it here with a change in pH of 3.62 pH units. Now stop for just a moment and think about what we did. We added 10 times as much acetic acid as we added hydrochloric acid. Remember here with hydrochloric acid, we added 1 millimole, and that dropped us from 7 to 3. With acetic acid, we added 10 millimoles, 10 times as much. But that didn't drop us to 3. It didn't quite make 3. It wasn't as good an acid. It did not dissociate to the same extent. Okay? Now, let's test our assumption. Was it fair to make these assumptions that we did? Let's see. Let's test our assumptions. We said at the beginning that the concentration of acetic acid in the end was going to be about equal to what we started with, which was about 0.01 molar. Okay? Now we know from this that the concentration of protons is equal to the concentration of acetate anions, which is equal to 4.18 times 10 to the minus 4 molar. Okay? And so if I now calculate what the real concentration of the undissociated acetic acid is, it would be 0.01 molar minus 0.0004 molar about, well, I guess I should 0.18, yep, 4 molar, which is equal to 0.0096 molar. So our assumption was accurate to within 4%.